Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to gravitation, and in this video we are going to discuss about the acceleration due to gravity, mass and average density of Earth. Okay, so in the previous video I think we discussed the gravitational force of Earth. Okay, and we discussed it with respect to three cases: at points which are far away from the surface of the earth, at points on or near the surface of the earth, and at points below the surface of the earth. So here for our discussion on acceleration due to gravity, which will only stick to this point, at points on or near the surface of the earth, because we want to determine the acceleration due to gravity near the surface of the earth or on the surface of the earth. Okay, very close to the surface of the earth. So we'll only stick to case 2. So let us say we have an object, let's say a satellite, which is very close to the surface of the earth, or it is on the surface of the earth. In that case, the separation distance between that satellite and earth, it will be equal to the radius of the earth. It will be equal to the radius of the earth if it is on the surface of the earth, or if it is very close to the surface of the earth, it will be almost equal to radius of the earth. Here we are considering earth to be a homogeneous, uniformly distributed mass distribution sphere of mass capital M, and the mass of the satellite, it is small m, and with respect to the size of the earth, the satellite behaves as a point mass. So we discussed that the gravitational force acting on the satellite, it will be directed towards the center of the earth as per Shell theorem, and the value of that gravitational force, it will be equal to, as per Newton's universal law of gravitation, F is equal to G capital M small m by r square. G is the universal gravitational constant, capital M is the mass of earth, small m is the mass of the satellite or the point mass, and capital R is the separation distance between the two objects, earth and the satellite, which is very close or on the surface of the earth. So here when the satellite, it is moving very close to the surface of the earth, when it is very near the surface of the earth, it will experience acceleration, which is called as acceleration due to gravity. Okay, the acceleration experienced by the object in the influence of Earth's gravitational pull. So that is given by F is equal to mg. Okay, this Newton's second law. According to Newton's second law of motion, F is equal to mg. Small m is the mass of the satellite, g is acceleration due to gravity. This is experienced under the influence of this gravitational force. F is equal to G capital M small m by r square. This gravitational force exerted by Earth on this satellite causes this. We are just expressing it in the form of Newton's second law, F is equal to mg. So we want to determine the expression for small g, acceleration due to gravity. So here we'll equate this equation with this. So we'll get mg is equal to m small g is equal to capital G capital M small m by r square. So here small m will get cancelled, so we'll have acceleration due to gravity small g is equal to capital G capital M by capital R square. This is the expression of acceleration due to gravity on or near the Earth's surface. And experimentally we have determined its value, which is very close to 9.8 meter per second square. There are other values also, but here I am sticking with this 9.8 meter per square. I am not including the second, third, fourth decimal place. Okay, 9.8 meter per second square. This is the value. and this is the expression of the mathematical expression of acceleration due to gravity, which we have found out by equating this expression of gravitational force as per Newton's universal law of gravitation and Newton's second law applied to the point mass, the satellite. This. So we have got this expression of acceleration due to gravity. Small g is equal to capital G, capital M by r square, where capital M is the mass of Earth. Okay, capital R is the radius of Earth, also the separation distance, and capital G is the universal gravitational constant. Small g is acceleration due to gravity. Okay, so from here we'll determine the mass of the Earth. We'll try to find out the approximate value of mass of the Earth. So we have got acceleration due to gravity, g is equal to, small g is equal to capital G, capital M by r square. So we can write the mass of the Earth, capital M, is equal to small g, capital R square by capital G. Okay, this. Now we know the value of small g, acceleration due to gravity, 9.8 meter per second square. We know the universal gravitational constant, capital G, as per Cavendish experiment, and also the radius of the Earth, the approximate value of radius of the Earth, which is equal to 6.37 into 10 to the power 6 meter. So when we put these values, okay, when we put these values in this expression, we will get the value of mass of Earth, the approximate value of mass of Earth. So we'll put the values here. Mass of the Earth, capital M, is equal to small g, capital R square by capital G. We'll put these values and we will get this 9.8 into 6.37 10 to the power 6 square by 6.67 10 to the power minus 11. Okay, so we get the approximate value of mass of Earth as 6 into 10 to the power 24 kg. Now the value is 5.96 or 5.97 into 10 to the power 24 kg. So here we have just converted into round numbers, that is 6 into 10 to the power 24 kg. Okay, this is the mass of the Earth. Next is average density of Earth. So we have calculated mass, this. Then we are considering Earth to be a sphere, okay, solid sphere of uniform mass distribution, uniform mass density. So what is that value of uniform mass density? So density is simply mass by volume. Mass of Earth is this gr square by g, okay, small gr square, capital R square by capital G. Volume of sphere will be equal to 4 by 3 pi r cube, where r is the radius of Earth. So density will be equal to mass by volume. So we'll substitute these expressions. For mass we'll write small g, capital R square by capital G, and for volume we'll write 4 by 3 pi capital R cube. So we have expression of density of Earth as this, very important expression, very important formula. Okay, density of Earth is given by 3 small g by 4 pi capital G capital R. Small g is acceleration due to gravity, capital G is universal gravitational constant, R is the radius of the Earth. So we know all these values, small g, capital G and R, okay, this. So again, when we put these values in these expression, this mathematical expression, we get the value of average density of Earth, approximate value of average density of Earth. So 3 small g by 4 pi capital G capital R, okay, this. So we have, when we calculate it, it is coming around 5500 kg per meter cube, okay, 5500 kg per meter cube. So again I have approximated it, it is coming around something 5504 or 3 or something like that. So I round it off in terms of a round expression, it is 5500 kg per meter cube. This is the average density of Earth. Okay, so here, using the gravitational force of Earth, that expression using the universal law of gravitation and Newton's second law, first we determined the mathematical expression for acceleration due to gravity small g. Then using that we determined the approximate value of mass of Earth using the values of these values: acceleration due to gravity, radius of Earth, and the universal gravitational constant. Again using the same values and basic, the density formula, that is mass by volume, we determined the average density, approximate value of the average density of Earth. Again we are assuming that Earth is a solid sphere with uniform homogeneous mass distribution, uniform mass density. Okay, under that assumption, so the average mass density, it is equal to this. The mass of the Earth is equal to this approximate value. Again I'm repeating, these are approximate values, not accurate values, and this is the acceleration due to gravity. Okay, so here we have done it. Okay,